Right.
Yeah,
So,
please
as
proceed.
it was introduced, so my topic that I'm going to talk about today is on the concept of sliding mode control. This will be a quite a brief introduction, something like a bird's eye view of the topic. I'll not go in too much into the mathematical details. I'll only go to the depth that may be necessary. And what I would encourage is two things. So, if at any point in the lecture, if anybody feels that some concept is uh, unclear, okay, what has been presented, then please do interrupt me, and I can clarify this. Okay, what I would uh, not want you to do is ask questions of topics that I have not talked about. Okay, so I have put whatever from my experience, what are the relevant topics. I put it like a chain. Okay, so I would try to cover all those things, which are major points of interest for anybody who has started working in the field of sliding mode control. Okay, so let me proceed with my lecture. Okay, so again, what would this lecture concentrate on? It would give a basic understanding of the concept of sliding mode control. Definitely, some mathematics would be there. No particular algorithms would be explained too much. Okay, and who would be interested in this? Would be interesting to people who are just learning sliding mode control, okay, or at least want to learn about control strategies, the concept defined control strategies that are a little more complicated than PID controllers, or want to work in systems that are more than second order. And what is the background that is expected out of this is that there should be a basic understanding of the concepts of matrices, what are eigenvalues, what do you mean by stability in a systems, and of course, since you're talking about sliding mode control, a basic understanding is what is the concept of state space. So basically, a good background in a UG control course is necessary for to have a good understanding of what I'm going to talk about in this particular lecture. Okay? But even without that, you can understand most of what I'm going to talk in that lecture. What is definitely necessary is for you to understand or for you to have a good grasp of differential equations. So if you have a grasp of differential equations, then probably most of these lectures would be easy to grasp. Okay, okay. So let's go answer one of these questions at a time. First, we'll talk about what is this word of sliding mode control, okay, and just a bit of history on it. Then, how is this concept useful, okay, and what are the recent development? So, what I would do is that I will always in my lectures I would differentiate between the sliding mode part and sliding mode control part of it. Okay, right. So let's go into the a bit of history of this. So this is something that you are really familiar about. This you would see in any of the devices like a AC or a geyser or a heater. So there is a relay switch. Okay, you have an element that either heats or cools, and when a particular set point is reached or a particular region around the set point is reached, the device either turns on or turns off. Okay, this simply an on off controller. Okay, so now what you're seeing here is a peculiar phenomena. So there are two things. Let us say that this is of a actually this is of a motor, a generator. Okay. So what is happening is that when you apply uh, when you turn this device on, this the speed increases. Okay. Or actually, yeah, the speed should have increased in this manner, and when you turn it off, the speed should have decreased in this manner. But when you combine both of them, what is happening is that the speed is approximately maintained constant at some point. Okay. What is to be noted is that this behavior was not there in this graph or in this graph. Both of them are not constant. Okay, so the response doesn't have a constant response in them. Okay, however, the resultant is giving a constant behavior. Okay, so this is one thing that is happening. Okay, so let's keep a pin on that and let's proceed further. Let's take another example of this. Okay, this is the mechanical example, and this is basically a rudder of a ship which has a on-off controller with a dead zone. So the rudder is in one position or in the other position, and the funny part is that the response is something like this. So beyond, when it is at this position, there is a minus u. When it is at this position, there is a plus u, and in between it just gets stuck. There is a dead zone in it. So basically this also behaves in a manner like an on-off controller, and when it is switched between an between the on and off position, or actually the right and left position, the ship doesn't turn right or left, but it goes in a one particular direction. So there is, if the rudder was kept in one of these positions, the action would be that the ship just keeps on rotating, but a combination is giving me a trajectory, a motion in a direction that was different from either the left or the right control. Okay, again, the combination is giving me something that is something different from whatever was the performance that either the left or the right control could have given me. Okay, and now let's go a little further. And so this behavior, that is the combination of two structures of control resulting in something interested this group working in the Institute of Control Sciences in USSR, okay, in the early 1950s and 60s. This was a very, very large institute that worked on control system. There was a similar institute on mechanical sciences and all in the erstwhile USSR. Okay, and this researcher, Professor Emelianov, so he got this interested in studying this concept in a more mathematical format, in a more formal way, and that study that interest led to what was called as the variable structure control concept, and the core focus on it was that you vary the system structure, you vary the control structure, okay, and the aim is to achieve stability in a system where either of the control structures is not giving much of a stability in this. So this is already too many words. So let us go into a little mathematics of it, and let's get a more clarity on what is the meaning of this. Okay, so I had given you some really practical example without going into the mathematics. Now I am going into the mathematics of it so that you can understand that, okay, this does mean stability. Mathematically we can say that stability can be achieved from system where the constituent systems don't really talk about stability. Okay, so this is just a second order system. X double dot is minus ax, and this variability in the structure is brought by having two choices for a. One is a1, one is a2. A1 is a positive number that is less than 1. A2 is a positive number that is greater than 1. Okay, now if you try to plot the phase trajectories for x using a1 and a2, you get these two modes. Okay, so for A1 you get a graph that looks like this. Okay, for A2 you get a graph that looks like this, mode 2. Okay, but what we're interested in is combining both of them. Okay, what we will do is that we will try to combine, use A1 in some region, that is mode 1 in some region and mode 2 in some other regions. Okay, so mode 1 in these two regions, in the first and third quadrant, and mode 2 in the second and fourth quadrant. Okay, so until now it looks quite same. Okay, there doesn't seem to be anything remarkable, but let's say that you have a representative point that starts from this point. Now it moves along mode 1. Okay, but at this point it has to change to mode 2, so it has to go along this trajectory, then again on this trajectory, then again on this trajectory. Okay, what you will note is that if I had maintained mode 1, it would have gone like this. If it had maintained mode 2, I would have gone like this. There was no convergence, okay, to origin. Okay, only you had something that you can say is marginally stable. Okay, you only had a marginally stable system if you use any single mode. Okay, however, when you use a combination from the mode, what you are getting is that this point goes to 0, so you have asymptotic stability. What is asymptotic stability? Is that your state is going to 0 as t goes to infinity. But this was not there when you had used when we had used one of the modes, or any one of the modes. Okay, so both of the constituent systems were oscillatory and not asymptotically stable, obviously, but the combined system is asymptotically stable. So this is one of the properties, or one of the achievements that we can get if we use VSC properly. Okay, why do I say properly? Because I can switch the modes. Okay, I could have used mode 2 in these two regions and mode 1 in these two regions, then I'm not going to get asymptotic stability. I would get something that is quite the obvious opposite of it. So I'll get instability out of it. So if you use variable structure control intelligently, then you can achieve quite a good properties. Okay, so this property of asymptotic stability was not present in any of the constituent systems of this variable structure control. Okay, let's take another example. So we had taken a very tame example by not considering in unstable constituent system, because why do you use controllers? Because you want to stabilize the system, which would mean that originally the system is not stable. Okay, so let's take a system that is not stable. Okay, again you have this second order system, and you have a choice of alpha. Okay, which is there is a constant alpha now, and alpha can be positive or negative, means it can be plus alpha or minus alpha. Okay, and it doesn't matter whether you take the positive or negative choices. If you take the negative choice of alpha, you'll get x double dot is minus I x dot minus alpha x. This is equal to 0. Okay, you have two eigenvalues for this system. Okay, and denoted by this, and only this chi minus, or yeah, this chi minus root of chi square plus 4 alpha by 2, only this is stable. So there is one unstable mode here and there is one stable mode here, and the eigen directions of this are given in this manner. This is the unstable direction, this is the stable direction. but that hardly matters because the system, even with one unstable mode, is an unstable system. Let us see if the plus alpha choice is any good. So the plus alpha choice gives me two roots again, okay, but chi-square minus 4 alpha now, okay, because alpha being greater than chi-square by 4, this would give me complex roots, okay. So this is the imaginary part of it, which can be plus something into I and minus, and this being positive, he would mean that I have two unstable complex roots, okay. So the trajectory goes like this. Again, something that is not really very pretty. So both systems are unstable. There is only one stable mode out of the 4 modes that we have, okay, and that stable mode has this particular eigenvalue, okay. So what can we do about it? Let's say that you are employing VSC, and with the choice that mode 1 is when xs is less than or equal to 0, and mode 2 is when x into s is greater than 0. But what is s? S is this particular line. S is c star x plus x dot, where c star is chosen as minus lambda. Okay, so let's look at it in a diagrammatic fashion. Okay, so what is happening now is that let me take a different pen color so that I'll be able to look into this. Okay, so the point goes like this, and then it will go like this, and then it will go like this. Again, you are getting stability out of a system, out of a combination of two systems which were unstable. Okay. Something very similar to the first example that we had seen. Okay, but let's see if we can get a more interesting behavior. Okay, let's not use the C star, let's use another value of C, okay, which is less than C star but still positive. Okay, the way that you switch remains the same, only thing is that the definition of S, the line that defines S, okay, has changed. It is no longer this line, it is some line that goes in a more shallow manner. Okay, something like this. Okay, earlier it was going exactly along this stable eigen direction. Now it is going in a different plane. Okay, but what we have to see is what is happening at this transition. So when it is close to this line and in this region, then mode 1 is active, and you see that it goes towards, so you see this line, it is going towards this sliding line. Okay, so the representative point is pulled towards this sliding line when this variable structure control is used, when the system is in mode 1. What about mode 2? Again, you see that when it is in mode 2 also, it is being pulled to this line. Okay, so if you combine both of them, what is seen is that it is pulled along, it is pulled towards this line at all times. Okay, and once it comes along the line, what is happening? Once it comes along the line, you will have this equation being satisfied, this differential equation being satisfied. Okay, now what is the solution of the differential equation? You will have something like x dot is equal to minus c2x. This is a stable system, but we already had stability, but this is a stable first order system. We had started with a second order system, and the behavior that we are getting is a stable first order system. And it is obvious that the trajectories, okay, that the trajectories in a second order system and the trajectories in a first order system are definitely different. Okay. What you have here is that you will have a motion along this particular line. Okay. And motion along this line was not a part of this mode 1, it was not a part of mode 2. Earlier in VSC, what we had was that we had the trajectories in the VSC to be either in mode 1 or in mode 2, but new behavior like stability was realized. Now you have a new trajectory that is not present in either of the two original constituent systems. Okay, so you are able to generate new trajectories also. Okay. Now let us get to the question of what is sliding mode control. So let's define sliding mode control. Sliding mode control, sliding mode, not sliding mode control. I should make the distinction. So what is sliding mode? It's a motion of the system trajectory along a chosen line, plane, surface of the state space. Okay, so what is important is that it is a chosen line, and the control, whatever the control design that we are doing to achieve sliding mode, can be termed as sliding mode control. And till now we have seen that it is possible using a variable structure type of controller. Okay, so the last example, the unstable system example, you could have said that if you design like this, you get sliding mode. Okay, now what is the advantage of going through all this hassle? And as usual, let us take a very simple example, okay, but not so simple as a second order system. Let's take an nth order system and let us confine to linear time invariant systems. So there is an nth order system in a phase variable form, which would mean that x1 dot is x2, x2 dot is x3, and so on, and xn dot is this particular equation, which again is a linear combination of all the states and the input also. Okay, now what would happen when you do a sliding mode controller for this? Okay, let's say that you define a sliding mode sliding function. Okay, s is so much, and somehow, okay, and this would actually mean that xn is this one, and if you make s is equal to 0, so if s is equal to 0, then this condition should be satisfied. If s is equal to 0, then xn would be this one, okay, and xn dot will be this one. But what is so great about that? Let's look at that. Okay, now what is happening is that now when the system is on the sliding mode, the equation becomes so much. Okay, and when it was in general, it was like this. Now if you notice the difference, you will see that when the system is on sliding mode, there is no dependent on the dynamics on those original parameters A1 and A2. So you have something called as robustness. So if your C are designed properly and you're able to design a sliding mode controller such that sliding mode is achieved, that is such that S is made to be equal to 0, what you end up with is a system that when in sliding mode is completely invariant or completely immune to changes in this A parameters. Okay, so that is the robustness properties. Okay, now from this, let us say that what should be the main required properties that we should have. Okay, So for the sliding mode to be of any use, we should design a control that brings the system to the sliding surface, okay, and it brings the system to the sliding surface in a finite amount of time, and the sliding surface itself should be useful, like when you saw in the variable structure control case, the system should be stable when confined to the sliding surface. So system stability is one of the requirements. An unstable sliding mode is not a sliding mode at all. So I can design a sliding surface that looks like this, x dot minus x is equal to 0, okay, but this is not sliding mode, okay. Mathematically it may look as if, yeah, you would be able to design a control that achieves this, but what is the use of it? You are making the system unstable, okay. So system stability when confined to the sliding surface, and the second requirement is that the sliding mode should not take forever to start. So asymptotic convergence is not good enough. That is, if you have a if I plot the graph of time versus the sliding surface, it should not look like this. This is not acceptable, or it should not even look like this, where it goes to 0, 0x or s is equal to 0 as t tends to infinity is not acceptable. So s should become 0 at some finite time. Okay, so let's handle each of them separately. First, consider the design of the sliding surface. Again, let's start with the very simple case of a system in which there is a single input, okay, and you design a sliding function, okay. The sliding function is a linear combination of the system states, so something of this structure, okay. Now when confined to this structure, the system should be stable, so that is why we want to design a sliding surface, okay. So when confined to this structure, s is k x1 plus x2 equal to 0, which means that x2 is minus k x1, okay, from which we can say that the dynamics of x1, that is substituting the value of x2 in this equation, will have something like this, okay. Does this equation looks similar? Actually, if you had remember, you would have seen something like a plus bf. This is the design of a controller for a system x dot equal to ax plus bu, where the controller u is equal to fx, okay. So this is very similar to state feedback controller design. So if you have techniques by which you can design a state feedback for a system like this, okay, like x dot equal to ax plus bu, then you can also use the same techniques to design a sliding surface, okay, for this sort of systems, okay. Okay, incidentally, this structure is called as regular form, and usually when you are designing a sliding mode controller, you bring the system to the regular form and then do the design, okay. And it is just a bit of mathematical jugglery, and not something that really requires investigation, okay. So how to design the surface? If the k is designed so that the eigenvalues of this thing a11 minus a12k are only on the left half plane, okay, and this, if it is achieved, obviously the system with x1, that will be stable, but x1 and x2 are related by this linear relationship, so dynamics of x2 will also come out to be stable, okay. we have taken this linear surface, okay, and confined to this linear surface, the system dynamics are stable. So the sliding surface design is clear to some extent. However, we should remember that the linear surface is just one of the choices. It is not necessary that S is a linear function of X. It can be a nonlinear function of S. The only requirement being that confined to S is equal to 0, the system dynamics should be stable. Okay, that was the surface design. How to come to S is equal to 0, that is the second requirement. Okay, the sliding mode should start, that is S is equal to 0, should be achieved within a finite amount of time. Okay, so let's split this requirement a bit further. The sliding mode should start, okay, and it should start in finite time. So what do you mean by the sliding mode should start? Which would mean that if S is greater than 0, it should decrease, okay, and S is less than 0, it should increase. Okay, so when S is greater than 0, S dot should be less than 0, and when S is less than 0, S dot should be greater than 0. When S is equal to 0, we'll handle that separately. Okay. So what we have here is that S times S dot should be less than 0. Okay, this is very similar to a condition of Lyapunov stability, but anyway, we'll look at this. So this is called as the reachability condition. So whenever you have SS dot less than 0, what you are assuring is that S is moving towards S is equal to 0. Okay, so this is the reachability condition. This may be a little off. So you have a sliding surface in a second order system. You have a sliding surface like this, and the trajectories are moving towards the sliding surface. Okay, let's take one example and see whether what's the case with this. Okay, so let us have a control that ensures that S dot is minus S. Okay, of course SS dot is less than 0, or SS dot is minus S square, which is definitely less than 0 for all non-zero values of X S. Okay, like actually this being a first order differential equation, you can actually solve it. So what you end up with a solution, S of t is e to minus t, S of 0, and of course S of 0 we have to assume not equal to 0, or else it starts from the sliding surface itself, which is not very exciting. Okay. So but the really bad point is that now S of t is 0 as t tends to infinity, and for no finite value of t will you have S of t being equal to 0. So what is the conclusion of it? Is that merely satisfying SS dot less than 0 is not enough. Something more strong is necessary. Okay. And why is this not enough? Because it cannot assure that sliding mode starts in finite time. You want that assurance. Okay. So the reason for that is when S becomes very close to 0, this linear relationship is going to slow down S by a lot, and that is why finite time convergence is not not achieved. A stronger condition is required. Okay. So let's say, so if I want to go from point A to point B in finite time, so there is AB. If I want to go from point A to point B in finite time, and it's a distance d. Okay, the sure shot way to go in finite time, okay, that is if I have maximum limit of time, okay, then you have a minimum speed. Okay, if I want to go from A to B in within some time, then I should have a minimum speed beyond which I should run. Okay, and if I have a minimum speed, then it assures that there is a maximum time limit within which I can reach. And the same or a very similar concept is being used here. So what we are doing is that we are putting a lower limit on the magnitude of S dot. Okay, and this lower limit is quantized by some quantity eta, and this modification of the reachability condition is called as eta reachability. Okay, so this S as a minimum rate of convergence, and this is the what you call a graphical representation of it. What is so S versus S dot plot? It can be in this region. What is to be noted is that near S is equal to 0, there is a discontinuity or not in S dot. Okay, so whatever was the equation describing S dot, there would be a discontinuities in, there should be a discontinuity in one of those components. Only then this can be achieved. At least the eta reachability can be achieved only with the discontinuity in it. So if you go in a more general fashion, okay, if you have a system where you have two modes, okay, and one is a positive, one is the, let us say one is for corresponding to S less than 0, one corresponds to S greater than 0, then we have not defined what will be the condition, what will be the dynamics at S is equal to 0, and this is actually achieved by something called as a continuation method that was proposed by this researcher Filipov. Okay, I'll not go into the details of this. It basically says that you have to design a sliding surface S such that confined to the sliding surface, this complicated dynamics, this should be stable. Okay, and it also says that this is a combination that will this is the equation, this is the motion described on the sliding surface. Okay, okay, now what we had was something like S dot is greater than, or magnitude of S dot is greater than eta. Okay, this is not a very good condition or information to have. It's like saying that you have up to 50% discount. We really don't know what is the exact amount of discount. So, but we can't say that. So if you have a system, if you want to design a controller, you want U to be equal to something. You don't want U greater than or U less than equation. This doesn't give me enough information about what is the actual control to be applied. Okay, so to be able to do that, what is done is that we have come up with this reaching law approach where you relate S dot and S by equations which will ensure that S dot is less than minus eta S. What was that? Yeah, minus eta mod S, something like this. Okay, and for that what you say is that S dot is generally has a structure of minus q fs minus k sin s. This is what which gives discontinuity in my in this S dot variable. Okay, so let's proceed a little further from this, and these are a few example of it. The simplest one is this, just using the signum term, S dot is minus k sin s, and or the constant or proportional rate, you add a minus qs, or a power rate reaching law where you say that S dot is this one, okay, where alpha is a value that is less than 1. Okay, Now, what will be the control signal when this is applied? Let us take again the proportional plus constant S dot as this equation. Okay, but S is C transpose X, so S dot is C transpose X dot, which has this expansion. Okay, now if you solve for U from this, you get U to be of this nature. Okay, now what is necessary now is that C transpose B should not be equal to 0. Okay, okay. So this C transpose B not equal to 0 basically means that U appears in the first derivative of S. U appears in S dot. Okay, and U appears in S dot, E would mean that if I try to define the transfer function between S and U, okay, I'll get a transfer function where the numerator is n minus 1 degree and the denominator is an nth degree. So the difference in these degrees is 1, and that is why these systems are called as relative degree 1 system. So this relative degree concept will become handy a little later in the chapter. That's why I'm bringing it here. Okay, and in one of the reaching laws I had explained earlier, let me put it here. Okay, one of them doesn't satisfy one of the properties that I uh, mentioned earlier. If you can find out, I'll be happy. Okay, but there is a discontinuity in what we have seen is that there is a discontinuity in S, and there is a discontinuity is in the control also. Okay. So there is, so near C transpose S is X equal to 0, that is near S is equal to 0. What is happening is that the control goes from one point, it is jumps to other points across S is equal to 0. When S is less than 0, this is minus K, and when S is greater than 0, this will be plus K. Okay, so there is a sudden shift in the control. The control is discontinuous. Okay, and theoretically, therefore, there should be a switching between these two stages at an infinite frequency, but with zero magnitude. However, practically this doesn't happen. Your actuators, whatever actuators that you are using, are physical practical systems, so they have their own bandwidth. Okay, so they can't switch at infinite frequencies. What would happen is that they will switch at some very high frequency, the maximum possible frequency at which they can operate, and they will switch at a not with zero magnitude, with a non-zero magnitude. Okay, so when what you expected was something like this, what you get is something like this. Okay, this looks smooth, this doesn't look smooth. Okay, and this is undesirable, and this phenomena is what is called as chattering, and that wherever you have systems where this high frequency is going to cause problems, the chattering is going to definitely cause problems, and in some system really serious problems also. Okay, so what you expect in ideally is a behavior of the representative point looking like this. What you end up with is a behavior that looks like this. Okay, but so what? So let us, but in, so if you have a physical system and if you are using sliding mode controller and the system by chance has quite a few mechanical components in it, what you will end up with is that you will end up actuating the high frequency modes of that particular system, which are usually not considered in the models. Okay, so they are unmodeled high frequency dynamics in the system. Okay, and the controller performance degrades, and more seriously, what would happen is that the high frequency can cause mechanical wear in the system. So the picture that you're seeing is actually the a modified video, okay, of the working of a engine, and the video modifies, and by sort of amplifying or by amplifying the vibrations in the system. Okay, so you see that areas like this, okay, here there is a vibration, so there is a high frequency vibration here which are actually being amplified here. Okay, so these joints over time will get worn out, and during the operation, during the normal operation, we will not notice anything. Okay, so the thing is that a chattering is going to cause high frequency dynamics to be excited and cause mechanical wear. Not really good. And the reason that the chattering even exists is because you are using this sine term, a signum term, and the control changes very abruptly across this. Okay. And what can be the solution? Don't use the signum term. Use smoother functions where there is no abrupt change. Okay. So we can reduce chattering by sort of relaxing the movement along the sliding surface condition. What we end up with, something that is almost sliding mode, very close to sliding mode, but not really sliding mode, something which is called as a quasi-sliding mode. Let's take a few choices for it. So what you can doing is that you are replacing the sine term with something that is more smooth here. So this is a saturation function based control where you have a band within which it behaves linearly, and outside the band it behaves as if it's a switch. Okay. This is called as a boundary layer technique, and if you look at it, so you have not just the saturation function, you have more choices that sort of approximates this with something that is smooth, either the saturation or the hyperbolic, or there may be other choices also. Okay, so looks like the problem is solved, but really the problem is not solved. Let's see why. Okay, you have a motion using the boundary layer technique. The motion becomes like this rather than something that looks like this. Okay. This anyway has become very close to unachievable now. But anyway, the advantage is that chattering is reduced. Okay. But let's take a step back. Why did we go? So you started with a linear system. Okay, original system was a linear time invariant system. What we are introducing is either you are getting a signum term which leads to chattering, okay, or to handle that you are using the saturation or the tan hyperbolic function, no chattering. Okay, good. But why did we bring this sine term in the first place? Why did we bring SMC, which basically this is a nonlinear term? Okay, why was this nonlinearity brought in the first place? Okay, the nonlinearity was in the first place because we said that when the system is confined to the sliding surface, there is robustness. S is equal to 0 is robust. That is why S is equal to 0 should be achieved in a finite time. Okay, if you go back, you will see that it never reaches S is equal to 0. It goes into the band, it is very close to S is equal to 0, it is never reaching S is equal to 0. So all these robustness properties for which we had gone through so much of hassle is not achieved. Okay, so technically sliding mode is not there at all. Okay, remember that reachability condition, that it should happen in finite time. S dot less than 0 was not enough. S tending to 0 at t tends to infinity was not enough. Something more strong was desired. And what is actually desired is that this relationship be satisfied. This is called as a non-Lipschitz function. Okay, it says that if you make the okay, so what for yeah, so this is this what should happen is that the ratio of s dot to s should tend to infinity as s tends to 0 and ss dot should be less than 0. Okay, so this is what we want, and this is a non-Lipschitz condition, and that should get satisfied, and it doesn't get satisfied in case of the uh, what do you say, the tan h and the saturation function, the smoothing functions, and that is why what we end up with is a situation where the sliding mode is not achieved in a finite amount of time. Okay, and we lose the basic property. Okay, so we had started with finding a control that would be robust, okay, and relatively simple. We ended up we ended up finding that the implementation of that control will require a discontinuous signal, a relay, and the relay would cause chattering. Chattering can be reduced by smoothing the sine function, okay, but then in the process we lost the basic thing of robustness. Okay. So something has to be taught about. We have to think about it, that whether we can retain robustness, okay, while having no chattering. Okay. So this was one of the questions that was plaguing people working in sliding mode control. Okay, and later solutions were found. But let us say, let's keep this aside, the chattering problem, let us keep it aside. Okay, and let's concentrate on what are the actual conditions. So when confined to the system should be stable when confined to s is equal to 0, that is definitely there. The system, the control should be such that it moves the state towards the sliding surface, okay, and it should do in finite time by satisfying this non-Lipschitz condition. Okay, so that was there, but this non-Lipschitz condition is leading to discontinuous control. Okay, but can it have other solutions also? That is something that researchers were looking into. Okay, but then this is again 20 years old thing. Okay. But there was one thing, that is, we had talked about parameter robustness earlier. What about disturbance rejection? How will sliding mode react to disturbances, external disturbances coming into the system? Okay, and what is the meaning of sliding mode when the dimension of u is greater than 1? The earlier example that we had taken was only a single input system. Okay, so you have seen that the parameter robustness was there. Okay, and we can also say that if you have disturbances that come through the input channel, then to confine to the sliding mode, okay, the equations don't really change. So when the system is confined to the sliding mode, again the disturbance is not appearing, the disturbance is not affecting the system. So as long as the disturbance is going through the input channel, which is technically we call as mass disturbance in all sliding mode literature, it is completely rejected, right? And what if there are more than one input? Okay, that is, the dimension of u is greater than 1, okay, which would mean that this x2 has more than one element, and this s, okay, instead of s is equal to something like ax1 plus bx2, okay, you will have multiple components in S1, and this K matrix is the K is a matrix rather than a one row vector. Okay. And basically this would mean that, so if you have an nth order system with one sliding surface, this sliding surface as such is a surface of dimension n minus 1. So if you have a second order system, okay, one input, so sliding surface is a line. Okay, now if you have a third order input, so third order system and one input, this sliding surface would be a plane. Okay, now there are, if you have a third order system with two inputs, you will have two planes, and eventually the sliding surface is actually two intersecting planes, and the objective is whatever you want it to be. Okay, so basically in a multi-input system you have more than one surface, and ideally what you want is to go to the intersection of both of these surfaces. Okay, and this intersection, the way that you proceed to the intersection can be that you directly go to that intersection, or you go to one surface and then travel along that surface to go to the intersection. You can again, you can go from surface to surface in a predefined order or by first approach. Okay, so when you go directly to the intersection, it's called as eventual sliding mode, and when you go surface to surface, it is called as an ordered sliding mode, and you can have fixed order or free order. Okay, and in eventual sliding mode, if you see it graphically, it looks like this. So it doesn't really, once it approaches the surface, it doesn't really care to stay on that surface. All it wants is to go to this intersection. Okay, and in ordered sliding mode, there is a particular order in which it approaches the sliding surfaces, and in unordered or a free order sliding mode, there is no particular order. Okay, and in any case, the general structure would look like this, and this, of course, due to the limits of perceptions that we can see, I can only show this for systems with a third order system with two inputs. And however, mathematically, this can be that the input, there is the order of the system can be fifth order, sixth order, the number of inputs can be 3, 4, and still the sliding mode will happen. The only problem is that we will not be able to visualize it, at least graphically. Okay, so we have seen that matched uncertainty can be handled very efficiently by the sliding mode controller. The system behavior while on the sliding mode can be made completely independent on the matched uncertainty. However, in reality, unmatched uncertainty is much more common. Okay. What is unmatched uncertainty? First of all, what is matched uncertainty, and why can we intuitively understand how sliding mode is achieving this? It's like saying that you are playing tug of war. Okay, so you have disturbances on one side and a control on one side. Okay, by saying matched uncertainty, you are saying that the disturbance is acting in the direction in which the control is acting. So they are in the same direction. They are along the same line. So if the disturbance is trying to pull, the control can pull back and maintain some sort of an equilibrium. Okay, so they are pulling against each other, and the main equation and a balance can be maintained. However, what if the push, the disturbance acts in a direction that is other than this? So what you have here is that the control is ready to act in this direction, but the disturbance is coming in this direction, so the control can't do. So you can, so in a tug of war, like you're having a tug of war match and somebody pushes you from the side, you have not prepared for that, so you'll fall down. So that would mean, but this sort of disturbance exists in many practical systems. And what is to be remembered is that the unmatched uncertainty cannot is an uncertainty component that is not coming through the input channel, and it cannot be compensated for by any sort of input. Only you can only hope to minimize it, okay, by an appropriate control, by effectively removing the matched, okay, and only minimizing the unmatched disturbance component of it. Okay, so there are some literature on minimizing the unmatched disturbance, but the amount of literature on unmatched uncertainty is much less than the amount of literature that handle matched uncertainty. Okay, and we have seen two things. Okay, till now we have seen that sliding mode is robust. Okay, but chattering was there. Okay, so what we needed is that S dot. Hello.
Okay. No. It's
It's
perfectly
fine.
fine.
Okay. Right. So yeah, so the chattering was there, and the chat. So what we needed was S dot to not to be discontinuous. Okay, we needed S dot not to be discontinuous to for chattering not to occur. Okay, and but we didn't have a clear-cut solution for this. Okay, so people worked on these things. So by improving the reaching phase, okay, that is how it approaches the S is equal to 0 surface, and on the sliding phase itself, how it approaches the origin. Work was done on both of these phases of the sliding mode, and two new branches came up. So the improvement of reaching phase led to something called as the branch of higher order sliding mode controller. So how it approaches the sliding surface, and the sliding phase improvement work on the sliding phase lead to something called as terminal sliding mode controller, where you improve the approach to origin. Okay, so yeah, let me use this example. So one of the one of the reaching laws that I had talked about had this sort of a structure. And alpha is between 0 and 1. Okay. Now, does this satisfy this eta reachability condition? You'd see that as S tends to 0, S dot also tends to 0. So the magnitude of S dot greater than minus plus eta, okay, is not getting satisfied here. Okay, but then why is this a valid sliding surface, a valid reaching law? Okay, and the reason for that is that when you do this, okay, rather, okay, so let's go into this a little on the higher order sliding mode. Let's define it so that then I'll go into the mathematics of it. Okay. So when s, so what we needed was that s of x should be equal to 0 in finite amount of time. Okay, and when the sliding surface is reached in finite time, then it should stay on it. The problem was that the chattering was happening. Okay, the solution is to somehow get a control such that s dot ds by dt also goes to 0 along with s is equal to 0 in a finite amount of time. This one was termed as is actually termed as second order sliding mode because s and s dot are made to go to 0. Okay, and if you extend it further for n minus 1 derivatives of s, what you end up with is the nth order sliding mode. Right. Now, what is the advantage of it? Since s dot is 0 and s dot is not discontinuous, there is no chattering problem. Okay, so the disadvantage, very easy to guess, is that the solution is not very straightforward. Okay, so this higher order sliding mode or a second order sliding mode has come up with two different strategies. One is for strategies where the system that or the sliding function is of relative degree 2. I had talked about the relative degree concept briefly earlier. Okay, that is the input appears in the second derivative of the sliding function, and in this case the input is discontinuous. However, again there is no chattering in the states, and if you plot the sliding surface sliding function versus its derivatives, you have something like this. You see that both of them are actually continuous. Okay, and there is another algorithm called a super twisting algorithm, okay, which actually operates on systems where the system is of relative degree 1, that is the input appears in the first derivative of the sliding surface sliding function, and the solution is that instead of designing you design u dot and make the discontinuity shifted to u dot, okay, or something like this. So you have a component u1 and u2 has no discontinuity in it, but u1 dot has discontinuity in it. Okay, again here in this case what will end up is that the input is continuous and the derivative of the sliding force is also continuous, sliding function is also continuous, and hence there is no chattering. Okay, this is a brief view of it. Okay, I'll skip this. This is not really interesting. No? Okay, so that was one case where you are tuning how the system approaches to the sliding surface. Okay, now how is the behavior on the sliding surface? Okay, so what if we design a sliding function such that when confined to the sliding function, the system reaches the origin or the equilibrium point, whatever we call it, okay, in a finite amount of time? Definitely, linear sliding surface of the form s dot x dot equal to minus kx cannot achieve this sort of a performance, because you will have something like x of t is e raised to minus kx into x of 0, and this component is not going to kt x equal to 0, and this component, the exponential component, is not going to 0 at any finite amount of time. Okay. The solution is something called as terminal sliding, okay, where you use a structure like this, which is really very similar to something that I had told earlier. Okay, the power rate reaching law. Okay, if you remember, I told that there is something wrong with this. This power rating reaching law doesn't satisfy the eta reachability condition. Okay, but it has some strong point in it. Okay, so what this basically does is when the system is close to origin, the rate of convergence is speeded up faster than exponential rate of convergence, and which this in turn will lead to finite time convergence of it. Okay, and you have a modification of this terminal sliding mode called as fast terminal sliding mode, where you have an additional term, okay, which will ensure that the convergence rate is also fast when the system is far away from the origin. Okay, so let's see what is happening here. That x dot equal to minus x. Okay, the x1 dot is equal to x2, and this is happening. And if you apply the non-Lipschitz condition on it, you will see that this tends to infinity. Okay, I can make the why this is finite time convergence, but I think that will be a bit too much of mathematics for this lecture, so I'm not doing that. But if you would believe me, I'll say that if you use this reaching law, what you have, not reaching law, if you use the sliding surface, you will have x1 equal to 0 in finite time, which when x1 equal to 0 and x1 stays at 0, x2, which is x1 dot, also is 0, and so the origin is reached. And the origin is reached in a finite amount of time after the sliding mode starts. Okay, and this other part, x1 raised to beta, speeds up the response when x1 is far away from the origin. Okay, and this was only for a second order system, and we can extend this to higher order systems also by nesting the different sliding surfaces. You can define S0 is x1 and Si based on Si minus 1. So S0 is x1, S1 is x1 dot plus alpha 1 x1 raised to gamma or something like that. Okay, and S2 would have S1 here. Okay, and so it goes to it will end up with Sn minus 1 is equal to 0. So first it will have Sn minus 1 be equal to 0, then Sn minus 2 being 0, and finally S0 goes to 0, and all of them happen in individually in finite amount of time, so with t1, t2 and so on. So at the end, the entire system, the entire nth order system can be made converge to the origin in a finite amount of time. Okay, so that is the concept of terminal sliding mode. So those were the different aspects of sliding mode that have been under research until now. Okay, and these are the few references that you can look into if you are still interested to work in it. So Utkin had written a seminal paper on variable structure systems in sliding mode control in 1977 in transactional automatic control. Okay, and there was a survey paper by Gao and colleagues on variable structure control in 1993. This actually gives a more broad picture of the different aspects of sliding mode control. Okay, the invariance condition and the effect of sliding mode on matched disturbance can be seen in this paper by Drazanovic. Okay, and this is a very good book by Edwards and Spurgeon on when you're trying to study about sliding mode control, and more importantly trying to code different aspects of it, like the sliding surface design or the controller design in case of LTI systems. Okay, and if you are interested in learning about higher order sliding mode, you have a paper, not a paper, a chapter on this, okay, by Levant and Friedman. Okay, and on this terminal sliding mode, you have the initial work by Xinghao, Yu, and Man. That came in a workshop in 1996. Okay, so I will stop my lecture here. So if you have any queries, you can post.